Hello, everyone. My name is Liang, and I'm from the infrastructure team of DIDI Chuxing. Let's get started. With the rapid development of artificial intelligence in these years, GPU plays a very important role and is widely used. It is usually provided as the form of virtual machine instance by cloud service providers. For some technical reasons, creating a virtual machine with a pass-through GPU card is very slow, which is a common issue faced by all cloud service providers. Today, I will share you with a practice that how DIDI solve this issue. The agenda of my presentation contains the following parts. The first part is the background, and the second part will list the main issues slow down the creation of a virtual machine with a pass-through GPU card. The third part will give some details of the solutions, and then the effect of the optimization will be shown. The last part is the conclusion. In this topic, I will call a virtual machine without or pass-through PCI device as a CPU virtual machine, and a virtual machine with one or more pass-through GPU cards as a GPU virtual machine. Creating a CPU virtual machine instance is fast. It usually takes several seconds, while creating a GPU virtual machine instance with the same resource configuration is slow. It may take several minutes if the virtual machine has a large RAM. In most cases, virtual machine creation time is not critical. But in some interactivity scenario, a long virtual machine instance creation time means poor user experience and computing resource waste. Virtual machine creation time is defined as the time interval between QEMU process start to execute and the guest kernel start to run. It's divided into two parts. The first part is virtual machine initialization time, which is defined as the time interval between QEMU process start to execute and the vCPU start to run. The second part is BIOS execution time, which is defined as the time interval between vCPU start to run and the first guest kernel log is printed. The chart in the right shows the creation time of different virtual machine instances before optimization. Some factors like virtual machine RAM size, the type of GPU card, and the count of GPU cards will affect virtual machine creation time. You will be curious about the reason for the long time it takes when creating a GPUVM virtual machine instance. What slows down the creation process? To find out the reason, we can use perf to get the hotspot functions of QEMU process. The flame graph in this page shows the hotspot is in the core chain of core function, VFIO pin page remote. This page lists the main factors slowing down the virtual machine creation. The key factors is function VFIO pin page remote is slow. By debug, you will find some repeated VFIO DMA map and unmap for the same ILVA area, which makes things worse. Besides that, PCI device reset, management metadata initialization in QEMU and other asynchronous configuration will slow down virtual machine instance creation. I will describe these factors in detail. For VFIO pin page remote, there are two main issues make it slow. The first one is zero-out operation, which is required when allocating pages for user space. Zero-out page content will make sure sensitive information invisible to user space. Because page allocated may have been used by other process of the kernel and has sensitive information retained. As a solution, we introduce a new feature called pre-zero-out free pages to speed up page allocation. The idea is simple. Zero-out free pages in advance. Then when allocating pages, zero-out can be skipped. The second issue is VFIO DMA map pin memory in a page-by-page way. This results in too many page table entries access. As a solution, pin memory in bulk is used to reduce the cost. For pre-zero-out free pages, it is based on free page reporting. Page zero-out operation is done in a code work thread. After page is zeroed out, set the page zero flag in corresponding page struct. When page allocated needs to be zeroed out, check the page zero flag first. If it's set, zero-out operation can be skipped. When pages are free, page zero flag is cleared and the zero-out worker will be woken up. I have sent the RFC patch set to upstream. You can find the implementation details with the link in this page. I will not talk more about it. To make VFIO DMA map pin memory in bulk, we add two functions in kernel. They are get user city page and get user city page long term. They are corresponding to get user page and get user page long term. CT here means physical continuous. The new function will try to pin memory and get the information about a bulk or physical continuous memory. The chart on the right shows the different behavior of the new function and the original one. The new function will be friendlier to function we address get PFN and make its life easier to pin memory in bulk. To take more benefits, huge page should be used. VFIO DMA map is inefficient. There are two reasons for this. The first one is the same IOVA map experienced the map, unmap, and then remap procedure. It's unreasonable. To solve this issue, the mapped IOVA area information are retained in QEMU to avoid unnecessary VFIO DMA map and unmap operation. For the whole thing to work, VFIO IOMU unmapped DMA out control is only called when map a conflict IOVA area. Conflict here means a new added IOVA area, which is intersected with an already mapped IOVA area, but not equals to it. The second issue is inefficient IOVA area mapping update. For example, to change the attribute of a subregion of an IOVA area which is already mapped, the whole IOVA area needs to be unmapped first and then be mapped again. This will happen for an IOVA area containing the address of 1 mega. As a solution, the IOVA area is split into two parts. One part is below 1 mega, and the other part is above 1 mega. It can prevent high part IOVA area from being unmapped for modifications to the low part. For PCI device reset, one reset takes about 1 second, so it's a slow operation. There are two issues in QEMU. The first one, a device was reset twice during virtual machine creation. One is in function QEMU system reset, and another one in VFIO group get device FDIO control. Reset twice is redundant. One of them can be removed. The second issue is PCI device reset operation are specified, are serialized. If a virtual machine has more than one GPU cards, it will take more time to reset the device. Do the PCI device reset in parallel will be more scalable. And furthermore, make the PCI device reset in parallel with VFIO DMA map can maximize the benefits. For QEMU color model, there are some time-consuming operations which can be optimized. Third-page bitmap initialization is one of them. Virtual machine with pass-through GPU does not support level migration currently. So third-page login for a PCI bar specifying MMIO range is useless, which can be skipped. When PML is enabled, set EPT entries debit is the last time-consuming operation. It uses reverse map to get the EPT entries for setting the debit. Crossing all the reverse map entries are time-consuming if the virtual machine has a large RAM. During the virtual machine creation, most of the EPT entries are empty. So, crossing all the reverse map to find a few or effective EPT entries is not worse. This can be improved by making the reverse map cursor more efficient. For example, we can introduce a sparse bitmap mechanism, like HBitmap used in QEMU, to skip the empty reverse map entries. In our environment, we use a lot simpler way to solve this issue by counting the effective reverse map entries. The reverse map entries for memory slot can be skipped if its effective reverse map entries count is 0. This is not an ideal solution, but it is a balance between the benefits and the development complexity. There are some configurations which will affect the virtual machine creation time. They are listed above. CBOS boot manual has 2.5 seconds of timeout by default. If boot manual is unnecessary, please disable it. If Linux guest is used, The graph may configure a timeout for selecting different color. If it's unnecessary, please change it to 0. Luma memory policy will affect the speed of page allocation when some of the loads have memory pressure, so be careful with it. This page shows the QEMU process flame graph after optimization. You can find the hotspot we saw before has disappeared. And this page shows the accumulated time taken by some make QEMU functions. As you see, the time is reduced greatly after optimization. This page shows the GPU virtual machine instance creation time when different optimization method is used. Compared with CPU virtual machine instance, it takes a little longer. And this page shows the creation time of a GPU virtual machine instance with 1 GPU card and 48 gigabyte RAM. Before optimization, it takes about 38 seconds. After optimization, it only takes 3.3 seconds. The creation time is reduced by more than 90%. For GPU virtual machine instance with 4 GPU cards and 192 GB RAM, it is reduced from about 2 minutes to 4.4 seconds, which is reduced by more than 95%. The conclusion part. I have to point out words of optimizations are not limited to GPU virtual machine instance. They apply to virtual machine instance with other PCI pass-through device. And some of them apply to CPU virtual machine instance. About pre-zero-out free page, it has some limitations. Its current implementation is not friendly to huge TLB file systems. Extra work is needed for this case. And there is a cold case. If the free page are not zeroed out in time, it may lose the effect of boosting things up. So it's far from perfect. Our solutions have some pros. The first point is transparent to guest. Nothing needs to be changed for guest. So it's more appropriate for public cloud environment. The second point, DMA operation in BIOS state can be handled correctly. Other solutions based on parallel virtualization need some workaround to forbid DMA operations in BIOS execution state. About the GPU virtual machine creation time, there is some room for further improvement. We find the Linux memory management seems inefficient in device pass-through scenario. For example, all the features for page migration and memory overcommit are useless in this case. So it's possible to make things simpler and more efficient. Is in our future play. One more thing, we will contribute our work to upstream. That's all for my presentation. And this is my email. If you have any question which I can't answer online, you can send an email to me. Thanks. Bye-bye.